Hi guys, this is our first of 5 videos on 8th grade EOG review, and this video is on Number Sense, where we look at the properties of exponents, terminating, repeating decimals, rational, irrational numbers, scientific notation, and estimating square roots. So the notes sheet you should have looks like this. I'm going to break it down each little section on the next slide, so I'm going to go ahead and skip to that. So as I said, we are going to work on estimating square roots, exponents, classifying and ordering real numbers, determining if a number is rational or irrational, terminating and repeating decimals, and scientific notation. And the first one we're going to take a look at is estimating. Okay, so we are going to start with estimating square roots. It's the top left section on your page. And we are going to estimate the square root of 27. And 27 is not a perfect square. You have to memorize the list of perfect squares from 1 to 15. So 1 squared is 1, 2 squared is 4, then 3 squared, 4 squared, 5 squared, 6 squared, all the way to 225, which is the same as 15 squared. So 27 does not fall on our list. We know that's going to be somewhere between the two perfect squares, 25 and 36. So we need to determine the perfect squares on both sides of the square root of 27. So the square root of 27 is going to come somewhere in between those two numbers. So it's going to be between the square root of 25 and the square root of 36. We know the square root of 25 is 5, and the square root of 36 is 6. So the square root of 7 is somewhere between the integers 5 and 6. So we know that the square root of 27 is going to be 5 point something, and we need to figure out what that something is. So we're going to use it using this method. I've showed you other methods, but this one I think is a little bit easier. We're going to take our irrational number of 27, and I know it's irrational because it's a non-perfect square. And I'm going to subtract from that the lower perfect square, and the lower perfect square is 25. And that's going to give my numerator, and that's 2. And then we're going to take, for our denominator, the bigger perfect square, which is 36, and subtract from that the lower perfect square. And so we will get 36 minus 25. And that gives us 11. So now we need to change this 2 over 11 into a decimal, and that decimal is going to go right here. So we need to know how many times does 11 go into the number 2, and I'm going to put a decimal point and 2 zeros. Well, we know 11 goes into 20 once. That's 11. And when we subtract, we get 90. 11 goes into 98 times, and that's 88. And when we subtract, we get 2, and we can stop there. So our decimal for estimating our square root is 5 and 1800ths. So where did the 5 come from? The 5 came from the lower perfect square. The 18 came from dividing the difference between the irrational number and the lower perfect square, and the bigger perfect square and the lower perfect square, and changing that fraction into a decimal. Okay, moving on to the next section of exponents. These rules, I believe we even maybe have done a foldable with this. I believe this was part of our quadratics unit when we went over this. So these are just the general rules for exponents. If we're multiplying two numbers with the same base, we just add the exponents. So the general rule is a to the m plus n. I'm going to pause the video and go ahead and write down what you remember from this, and then check back on the video, and then we'll go over some examples. Check your answers right here. These are the general rules, and then we're going to go through some examples. So if we have two numbers with the same base, 2 to the 4th times 2 to the 5th, we just add those exponents, and we get 2 to the 9th. Same thing with if we had, let's say this was inside parentheses, we had 2 to the 4th to the 5th. In this case, we would multiply these two together, and we would get 2 to the 20th. A times B, let's say we had 2x, and we had that to the 3rd power. Get my marker to work, there we go. We would get 2 to the 3rd times x to the 3rd, and we could Okay, and same thing with division. If we have a fraction to a power, let's say, for example, that we have 2/3 to the 5th power. That's the same as 2 to the 5th divided by 3 to the 5th. And we could write out, or we could simplify 2 to the 5th and 3 to the 5th, but for our purpose, we'll just leave it right there. And then finally, the last three. If we have numbers with the same base again, and let's say we have x to the 6th divided by x to the 1st, we would just subtract those exponents and we would get x to the 5th. Now this is the one that has caused people grief. If I have x to the -2 power, or any negative number, I flip it over. If it's make it a fraction, the denominator becomes the numerator. The base stays the same, the exponent becomes positive. And the same of that would be true if I had one that was going the other way. Let's say I had 2 over x to the -3. I would also flip that fraction. However, the 2 is going to stay where it is because it has a positive exponent, and this would be 2x to the 3rd over 1. And then anything raised to the 0 power, 4x squared z to the 10th to the 0 power is going to equal 1. Okay, moving on to our next one, irrational versus rational numbers. It's basically this simple. A rational number can be written as a fraction, and that includes terminating and repeating decimals. So I can write 0.3 repeating as 1/3. I can write 25 hundredths as 25 over 100. If it's an integer, -16, I can write that as -16 over 1. So it can be written as a fraction. That means it's rational. If it cannot be written as a fraction, which means it doesn't make sense, then it's irrational. And those are non-perfect squares, like the square root of 27. And if we worked out the square root of 27, I believe, on the calculator, which is what I did, it came out to be 5.196152. And our calculator stops after a certain number of digits, but this one goes on forever, so that makes it irrational. Pi cannot be written as a fraction. And then if we have numbers like 1.678, and you see these dots here, there's no pattern to them, there's no repeating numbers, so therefore it is irrational. Okay, moving on to classifying and ordering, comparing real numbers. So this is a fairly simple one, but again, has to be done without a calculator. So before we can classify these numbers, we need to get them all in the same language. So we can change them all to fractions, or we can change them all to decimals, and then we have to compare. But the easiest thing to do is to change these all to decimals. So again, without the use of a calculator, -11 divided by 6 is -1.83 repeating. The square root of 19 is 4.36. Square root of 17 is 4.12. 6/5 is 1.2. And then this one's already in decimal form. So when we're putting these in order from, in this case, least to greatest, let's make sure you read, we want to put them in their original form. So if we're going least to greatest, the smallest one is this one, and that's -11 over 6. And again, I'm just comparing the decimal. Then we move up to number 2, which is 23 hundredths. And again, we're comparing decimals to decimals. Next is 1.2, which is 6/5. Then the square root of 17, which is 4 and 12 hundredths. And then the square root of 19. So again, when you're putting these in order from least to greatest, you need to put them back in their original form. But you're changing them to decimals so you can compare them all in the same form. Okay, last we have terminating and repeating decimals. Terminating decimals is exactly what it says. It terminates. So a decimal number that has digits that do not go on forever. So for example, 2, -2.6, 0.2145. Those are all terminating decimals because they don't go on forever. We know they don't go on forever because we don't have any dot dot dots after this. So repeating decimal repeats itself. It has digits that, well, it doesn't have digits that go on forever. It has digits that have a pattern. So, for example, 0.3 repeating is a repeater. If we had 0.1616, that is a repeater because I can see a pattern. If it's not a terminator or it's a repeater, we call that a non-terminating, non-repeating decimal, and that's irrational. Now, sometimes our calculator will round for us, like if we had the fraction 2/3, our calculator will round that to 0.67, but really it's just 0.6 repeating. And last but not least, scientific notation. So a couple of things about scientific notation. If this number right here is positive, that means our number is going to be bigger than 1. If that exponent is negative, that means our number is going to be less than 1. So we have a positive exponent. This number is bigger than 1. This is called standard form. And when we have our digits times the power of 10, then we call that scientific notation. So for example, if I had 5.3266 times 10 to the negative 3, I know that this is going to be a number that's less than 1, so I would take my decimal point and I would move it 3 places to the left. So that would give me 0.00532666. And this number is less than 1. And the most important thing about scientific notation is to know that if this is positive, your number is bigger than 1. If this is negative, your number has to be less than 1. And the other important factor to remember is when you're writing in scientific notation, the number in front of the decimal has to be, it is bigger than 0 but less than 10. So we can't ever have a 0 in that place. So the only place we're going to have to the left of the number we're going to have to the left of the decimal is 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. Our goal is to get the decimal point with only a number in the ones place, and then everything after that are the numbers that we're converting from standard form. Okay, now it's your turn to answer some questions. There is no Google form. You're just going to answer them on your paper. Place the following numbers in order from least to greatest. Remember, you have to give them all in the same form. And these questions, I'll remind you, are calculator inactive. These are the ones you will see on the calculator inactive section of the EOG. Okay, 1 down, 4 more to go. Have a good night.